Hi guys, I am solving the May June papers, 2023, paper 4.2. Having seen paper 4.1, I want also to take you through paper 4. My name is IBM, and without wasting time, I would like to take you to the question papers. So the name of the student is IBM. So you reduce the thickness. So I'll not go through the instructions, but this is May June 2023, paper 4.2. The paper is 2 hours. It is paper 4 A-level structured questions. The paper is 100 marks. I'll not go through the data, that is the constants. We are now used to these constants. The formula, we are now used to this formula. Question number 1, state Newton's law of gravitation. Of course, we know that Newton's law applies to point masses, so we can simply say that the force, remember this force is always attractive. So the force between 2-point masses force between 2-point masses is directly proportional to the product of the masses and inversely proportional to the square of their separation. So if you know Newton's law of gravitation, F is equal to G m1 m2 over r squared, product of the masses and the square of their separation. Satellite is in a circular orbit around a planet. The radius of the orbit is r, and the period of the orbit is t. The planet is a uniform sphere. Use Newton's law of gravitation to show that r and t are related by this equation here. Okay, so in my explanation, we know that the gravitational force provides the centripetal force. So I'll simply say gravitational force provides centripetal force. The gravitational force provides centripetal force. So in other words, I'm saying the force due to gravity is equal to the centripetal force. In that case, gravitational force is given by capital G. So capital M is the mass of the planet. So I'm going to consider small m to be the mass, the smallest mass. So I'll say G times capital M times small m divided by the radius of orbit, which is capital R squared, that is Newton's law of gravitation. Then the centripetal force is given by small m times v squared divided by r. And of course, I want to derive this expression here. So we know that v equals to omega times r, and omega is 2 pi over period. So this is 2 pi over the period times r. So that is v. So I'm now substituting. So g, of course, small m has already cancelled. So g capital M divided by r, 1r has cancelled with the square, is equal to v squared, which is going to be 4 pi squared r squared divided by t squared. So when you cross multiply, you will have that g capital M t squared is equal to 4 pi squared times r cubed as required. Earth may be considered to be a uniform sphere of mass 5.9 times 10 to 98 times 10 to the power of 24 and the radius 6.37 times 10 to the power of 6. A geostationary satellite is in orbit around the Earth. Use the expression to determine the height of the satellite above the Earth. Okay, so we can find the radius of the orbit by simply we have already seen that 4 pi squared times r cubed is equal to g m t squared. So it means the radius cubed is going to be g, which is 67 times 10 to the power of minus 11. The mass is 5.98 times 10 to the power of 24. Then the period, it is geostationary. The period is 24 hours because that is the time taken for one revolution around the Earth. That is 24 hours. So the period is going to be 24 times 3,600 to change it to seconds. But remember, this is squared. So I will divide this by 4 pi squared. So I'm going to find r. I'll first divide this, then I get the cube root. So 6.67 exponent minus 11 times 5.98 exponent 24 times 24 times 3,600 squared. So divide by 4 pi squared. Then I get the cube root. So cube root of the answer. So this is 4.23. 4.23 times 10 to the power of, that is 367, that is power 7. So that is the radius. So we want to find the height. The height will be the radius of the orbit minus the radius of the Earth. So that is 4.23 times 10 to the power of 7 minus the height of the radius of the Earth, which is 6.37 times 10 to the power of 6. So I'll just say 4.23 exponent 7 minus 6.37 exponent 6. So this is giving me 3.59. So this is 3.59 times 10 to the power of 7. Yes, that is the height. Gravitation is very easy. Another satellite is in a circular orbit around the Earth with the same orbital radius and period as the satellite in C. Same orbital radius, same period. Calculate the angular speed of the satellite in this orbit. So of course we know that angular speed is equal to 2 pi divided by period. So this is 2 pi because it has the same period as before. The period is 24 hours. So that is simply 24 times 3,600. Change it to seconds. So we have 2 pi divided by 24 times 3,600. So this is giving me 7.3 times 10 to the power of minus 5. So 7.3 times 10 to the power of minus 5. The unit here is, of course, angular velocity, that is radians per second. Radians per second. So rads per second, that is how we write it. Rad per second. Then despite having the same orbital period, they have the same period. The orbit of the satellite is not geostationary. Of course, for geostationary, the period is the same. The motion should be west to east. It should be above the equator. That is for geostationary. So the period is the same. Then they are saying, but they said the motion is not geostationary. Then that means these two are not satisfied. The question is two ways in which the orbit of the satellite could be different from the orbit of the satellite in C. So we can say the orbit is not equatorial. Orbit is not equatorial. The orbit is not equatorial. That is, the orbit could be polar. You could say the orbit could be polar. Instead of it being just above the equator, it could be moving in the poles. Number two, we said for geostationary it should be west to east. Since it is not geostationary, it could be east to west. So you can say orbit is not from west to east. You could say orbit could be east to west. Orbit is east to west. Okay, so it means it is not geostationary. If it is not from west to east and it's not above the equator, then it is not geostationary. Step one is of course, an ideal gas. The first thing to come into your mind is the equation PV equals to nRT. Any gas which obeys the equation PV is equal to nRT is considered to be ideal. So we shall say a gas which obeys PV directly proportional to T for all values of P, V, and T. Then you define the symbols. P is the pressure of the gas. Then V is the volume of the gas. And then T is the absolute temperature. So a gas which obeys PV is directly proportional to T for all values of P, V, and T is said to be an ideal gas. Or a gas which obeys the equation PV is equal to nRT, where P is pressure, V is volume, N is number of moles, R is the molar gas constant, and T is the absolute temperature, is called an ideal gas. State the temperature in degrees Celsius of absolute zero. So 0 Kelvin is going to be 0 minus 273 to change it to degrees Celsius, or 0 minus 273.15. So the answer is going to be negative 273.15 degrees Celsius. This is the more exact value of the absolute zero in Kelvin. A sealed vessel contains a mass of 0.0424 kilograms of ideal gas at 227 degrees Celsius. The pressure of the gas is 1.37 times 10 to the power 5 pascals, and the volume of the gas is 0.640 meters cubed. Calculate the number of molecules of the gas in the vessel. The number of molecules of the gas in the vessel. So number of molecules of the gas. So PV is equal to nRT. And remember, the number of moles is equal to the number of molecules divided by Avogadro's number. So when I substitute, you notice that PV is going to be equal to N over NA times RT, but R over NA is K. So PV is equal to N K times T. So it means the number of molecules is going to be PV divided by KT, where P is the pressure is 1.3 7 times 10 to the power of 5. The volume is 0.640 divided by K. K is Boltzmann's constant, which is 1.38 times 10 to the power of minus 23. It is given the list of constants. Then times T. The temperature is 227 plus 273, which is, I think this is 500. So times 500. So 1.37 exponent 5 times 0.64 divided by 1.38 exponent minus 23. Okay, divide by 500. I know body mass would affect my answer, so I have 1.27 times 10 to the power of 25. So 1.27 times 10 to the power of 25. That is the number of molecules. The mass of one molecule of the gas, one molecule. So this is the number of molecules, and a sealed vessel contains a mass of an ideal gas. So if this is the mass of the gas, which has this number of molecules, so we can say the mass of one molecule is approximate total mass of the gas, which is 0.0424 divided by the number of molecules, which is 1.27 times 10 to the power of 25. So I'll check my calculator. 0.0424 divided by the answer, approximately 3.34. 3.34 times 10 to the power of negative 27 kilograms. Then the root mean square speed, V of the molecules of the gas. So we know that the average kinetic energy of a molecule is equal to a half mass of one molecule, the mean square speed, which we derived, or you must have derived in your class, as being equal to 3/2 times kT. So since we know K, we know T, we shall use the other part of 3/2 times kT. So I want to find the root mean square speed V. So the root mean square speed, which is given as V, is going to be, I will divide by M. So this is going to be the square root of 3 kT divided by M, because the half cancels. So when I substitute, this is going to be the square root of 3 times K, which is 1.3 times, so 1.38 times 10 to the power of minus 27 times 500 divided by the mass, which is 3.34 times 10 to the power of, because it is of the molecules, the root mean square speed of the molecule. So of course I must take the speed of one molecule, the mass of one molecule. So this is times 10 to the power of minus 27. So 3 times 1.38 exponent minus, of course minus 27 has cancelled, I will not even consider it. 3 times 1.38 times the temperature, which is 500, divided by 3.34, then square root. So this is 24.89. Is it? No, this is 23, not 27. The speed is very small. It can't be 3 times 1.38 exponent minus 23, not 27, times 500 divided by 3.34 exponent minus 27. Then I find the square root. Okay, that is 2489 or 2490. So this is 2489.5, or approximately 2490. meters per second. Alternatively, we would have used, another student would use, of course, we know that PV is equal to 1 over 3 m n mean square speed. This one is given the list of formula. And of course, we know that if I get m times n, that is total mass. This is mass of the gas. Mass of one molecule times the number of molecules is the mass of the gas, which we already know as 0.0424. So I just substitute. So I will say V, which is the root mean square speed, is going to be equal to the square root of this, which is going to be the square root of PV times 3 PV divided by, that is 3 PV divided by the mass, divided by m times n. Remember, m times n is that, so this will be equal to, so this would be equal to the square root of 3 times the pressure, which is 1.37, I think, times 10 to the power of 5. The volume was 0.640 divided by total mass, which is 0.0424. Let me check. 3 times 1.37 exponent 5 times 0.64 divided by 0.0424, square root of the answer. This is automatically 2490 meters per second. So it's the same answer. The gas in B is now cooled gradually. The gas in B is now cooled gradually to absolute zero. On the figure, sketch the variation with thermodynamic temperature of the root mean square speed of the molecules of the gas. So we have already seen that the root mean square speed V is equal to the square root of 3 kT divided by m. So if the mass is constant, 3k is constant, means V is directly proportional to the root of T. What does that mean? If T equals to 0, V equals to 0. So when the temperature becomes 0, V becomes 0. So the graph goes to the x-axis. And when the temperature equals to 500, V is going to be V. So I'm plotting 500 against V. Around here, you use a ruler and verify. 500 against V, it's around that point. So, but V is directly proportional to the square. Let's just check a few numbers. Let's check what happens to, suppose T is equal to, let's say T is equal to 60. I want a number which is easy to find the square. T equals to 100. What is V? V is going to be simply the square root of, directly proportional to the square root of 100, which is going to be 10 if everything is constant. So it means this is T increases more rapidly with the V. That means the graph has a decreasing gradient. So the graph has a decreasing gradient. So that means I'm going to sketch a curve like that. That is the perfect graph. The graph has a decreasing gradient. So I'll sketch a curve like that. It is not a straight line at all because V is directly proportional to the square root. If it was V directly proportional to T, it would be a straight line. But since it is V directly proportional to the root of T, then it is a graph with a decreasing gradient. State the first law of thermodynamics. Of course, we know that the change in internal energy is equal to Q plus W. So just put this in words. So we shall say increase, because if this is positive, that is increase. Positive, that is energy supplied to. Positive, that is work done on. So we shall say, keeping the sign conventions, we shall say that increase in internal energy is equal to the work done on the system plus thermal energy transferred to the system plus energy transferred to the system by heating. That is the first of thermodynamics. I'm saying work done on because I've considered the plus conversion. Thermal energy transferred to the system because I've considered a plus conversion on Q. And I'm saying increase because I've considered a plus conversion on delta U. Okay, so the state of an ideal gas is continuously changed according to the cycle ABCDA shown in the figure. Complete the table for the changes A to B. A to B, that is constant pressure. B to C, that is constant volume, by placing two ticks in each row. A to B. So I'm going to just use a simple formula. The change in internal energy is equal to Q plus W. A to B, it is a compression. Work done increases. Work is done on the gas. Work is done on the gas. Work done on the gas is positive, by the gas is negative. So A to B, work done is positive. Then change in internal energy A to B, the work done is positive, and the state of an ideal gas is continuously changed to the cycle ABCD as shown. Okay, so the pressure is constant, the work done is positive because the volume decreases, the work done is positive. That is A to B. Okay, let me first leave that. I'll come back to that. Let's see B to C. The work done is 0 because the volume is constant. B to C, the work done is 0 because the volume is constant. Then energy, because this is 0, the work done is constant. Now let's use an equation such as PV is equal to nRT. So P to V, B to C, pressure increases, the volume is constant, but pressure is directly proportional to temperature at constant volume. Pressure is directly proportional to temperature at constant volume, that is B to C. Pressure is directly proportional to temperature at constant volume. So the pressure increases, meaning the temperature increases. But temperature is directly proportional to the change in internal energy, because temperature is the average kinetic energy of the molecules, yet the internal energy is the sum of the kinetic energy of the molecules. So the change in internal energy is directly proportional to temperature. If temperature increases, the change in internal energy increases, that is B to C. So B to C, internal energy increases. Now let's check A to B. A to B. I'm going to use the same expression. PV is equal to nRT. A to B pressure is constant. The volume decreases. At constant pressure, volume is directly proportional to temperature. The volume decreases, the temperature decreases. But remember, change in internal energy is directly proportional to temperature. If temperature has decreased, the change in internal energy has also decreased. So A to B, internal energy has decreased. So those are the 4 marks. And that is all. Hope I didn't miss anything in the table. No. First row, change in internal energy decreases. Work done positive. Okay. Use the first law of thermodynamics to describe and explain the energy transfers associated with one complete cycle, A, B, C, D. So I want you to recall that A to B, internal energy, the change in internal energy was a decrease. Then B, of course, C to B or B to C. B, this was A to B, B to C. The change in internal energy was an increase, I think. B to C, change in internal energy was an increase. Okay. Then let's check what happens to C to D. C to D. Now look at C to D. The pressure is constant, the volume is increasing. If you consider PV is equal to nRT, pressure is constant from C to D, pressure is constant, V is increasing. So volume increases, volume is directly proportional to temperature, temperature is increasing if the pressure does not change. So it means it means C to D, since temperature increases, it means the change in internal energy also increases because internal energy is directly proportional to temperature. The change in internal energy is directly proportional to change in temperature. If the temperature has increased, the change in internal energy increases if the pressure has remained constant in that case. So the internal energy increases. Then we can check D, C to D, then D to A. D to A, the volume was constant, the pressure decreased, and the pressure is directly proportional to temperature, so the change in internal energy decreased. Okay. So, but remember, total change in internal energy should be 0 for one complete cycle. Total change in internal energy should be 0 for one complete cycle. So let's now start explaining. Between from B to B, C, and I think C, there is no change in internal. There is no work done because there is constant volume. So we can start with that. There is no work done. On the gas in B, C, and is it B, C, and DA? There's no work done in B, C, and DA because the volume is constant. Since volume is constant, there's no work done since the volume is constant. So there's no work done. Remember, the change in internal energy is equal to Q plus W. For BC and DA, the W part is 0. Okay, so it means the change in internal energy is directly proportional to, is just depending on the amount of heat either added to or transferred to the system. Then, remember the net or total change in internal energy must be 0. The net change in internal energy must be zero. Total change in internal energy must be zero. Total change in internal energy must be zero. So, if A to B there is a decrease in internal energy, and B to C there is an increase in internal energy, it means heat has been added to the system. That's number one. In C to D, there is an increase in internal energy. That one is fine. Then in D to A, there is a decrease in internal energy. That means heat must be lost. D to A, there is a decrease in internal energy, which means Q must have been lost. But because the total internal energy must be zero, then it means what? The increase in internal energy, the energy transferred in C to D must be greater than the energy transfer in B to C, so that the total change in internal energy is going to be zero. So there must be an overall input of thermal energy into the gas. So we can simply say, since more work is done by the gas in C to D during expansion, C to D there is going to be more work done during expansion than B to C during the compression. More work is done by the gas in a CD, that is during expansion, than is done on the gas in A to B, that is during compression. So because total internal energy must be zero, then more thermal energy must be transferred along CD than along AB. So in overall, there must be an input of thermal energy into the gas. So there must be an overall input of thermal energy into the gas. There must be an overall input of thermal energy into the gas. So that will be the explanation for this part here. Remember, the total energy for a complete cycle must be zero. Total change in internal energy must be zero. Okay, let's check the next question. I think it's simple harmonic motion. Okay, the velocity v of the sphere varies with displacement x from its equilibrium position according to this equation here. So you compare this with v equals to plus or minus omega square root of x naught squared minus x squared, where x naught is the amplitude. Calculate the frequency of the oscillations. So we know that omega is equal to pi times f. So that means f is going to be equal to omega, which is 9.7 when you compare the equations, divided by 2 pi. So 9.7 divided by 2 pi, that is 1.54. Then show that the amplitude of the oscillations is 3.4 centimeters. So we are comparing the two equations. We notice that x naught squared is 11.6. X naught is the amplitude. So x naught squared is equal to 11.6. So it means x naught is going to be the square root of 11.6. So the units here are in centimeters, so that is fine. So square root of 11.6. This is 3.4 or 3.405, so that is 3.4. Calculate the maximum acceleration. Of course, we know that acceleration is equal to negative omega squared x. So if it is maximum, it depends on maximum amplitude. So maximum acceleration is going to be omega squared x naught, where x naught is the amplitude. So this is going to be 9.7 squared, then times x naught, which is 3.4. But remember, this is in centimeters, and we want the answer in meters per second. So I'll just say times 10 to the power of minus 2. So 9.7 times 3.4 exponent minus 2. So that is 0.33. This is 0.33. 0.33. If I had used here, a more significant figures, it could be approximately 0. Did I say 0.33? I didn't square 9.7. 9.7 squared times 3.4 exponent minus 2. So it is not 0.3, 3.2, approximately 3.2. So this is 3.2 meters per second. Okay. Sketch the variation with time of the acceleration A of the sphere. Of course, we know that the graph of acceleration against displacement is a straight line which goes through the origin. So, and the maximum acceleration is A naught. And remember, acceleration was maximum when amplitude is 3.4. So we just look for 3.4 from the graph. The scale here is 0.2. So 1, 2, 3, 4, 5. That is 3. 3.2, 3.4. So I'll just plot this. And then that is for negative displacement. This is negative 3.4. Then for positive 3.4, it is going to be negative acceleration, which is minus a naught. So of course for 0 it is 0. So that is a straight line. Just get your ruler and draw a straight line to the origin. So you make sure your graph does not go beyond this point here. It does not go beyond this point here. So make sure you plotted points stop here exactly where I'm circling. Okay, so that will be the graph to be a straight line for the origin. So I've plotted the points. I've plotted positive 3.4 against A naught. I've plotted negative 3.4 against A naught. Positive gives us negative, negative, positive. Then I've plotted 0, 0 to go through the origin. Then describe without calculation the interchange between the potential energy and the kinetic energies of the oscillations. Remember, total energy remains constant. So when at maximum, we know that at maximum displacement, let's first write the formulas. Potential energy is equal to, let me start with the kinetic energy, which is a half m omega squared into x naught squared minus x squared. Then potential energy is a half m omega squared x squared. So we want the interchange. At maximum displacement, that is when x is equal to x naught, kinetic energy is 0, and potential energy is maximum. So I will start with that one. At maximum displacement, when x is x naught, when I put here, when x is x naught, this becomes 0. The the kinetic energy becomes 0. This bracket becomes 0. So it means kinetic energy is 0. Then when x is equal to x naught, potential energy is maximum. Potential energy is maximum. Then at 0 displacement, that is when x is equal to 0. This was at x equals x naught. Then when x equals to 0, so we are saying at x, at 0 displacement, the reverse is true. When I put x 0 as 0 here, potential energy becomes 0. When I put x as 0, kinetic energy becomes maximum. So kinetic energy is maximum and potential energy is going to be 0 or minimum. So potential energy will be minimum. But remember, the sum of the two will always be constant. What is the constant here? E total. When I add the two equations, I will get a half m omega squared x naught squared, where all these ones are constants. So but the sum of kinetic energy and potential energy is always a constant. When I add the kinetic and potential, I'll always get a constant, even though as kinetic decreases, potential increases, and vice versa. Okay, so that is harmonic motion. Here is capacitance. Two capacitors A and B are connected into the circuit as shown in the figure. Capacitor A has capacitance C and capacitor B has capacitance 3C. So A is C, B is 3C. The EMF of the cell is V. The two-way switch S is initially at position X, and capacitor B is initially unchanged. State in terms of V and C expressions for the charge QA on the plates of capacitor A. So we know by definition capacitance is charge per unit potential difference. So we want the charge QA. The charge on capacitor A, capacitance is C, and when it is fully charged, the potential difference is V. So this is going to simply be C times V. So the answer is C times V. It is C times V. Then the initial energy stored in capacitor A. We know that energy is half times charge, capacitance times V squared. That is simply a half. Energy stored by a capacitor is a half CV squared. Then the two-way switch is now moved to position Y. The two-way switch is now going to be moved to position Y. Now the two capacitors are going to be in parallel. Okay. The two capacitors are going to be in parallel, so they are going to share the charge, which was on A. And charge stops when the PD across the two capacitors become equal because they are in parallel. So set and explain what happens to the charge that was initially on the plates of capacitor A. So we are going to say sum of the charge on A is going to be transferred to B, is transferred to the plates of capacitor B. So some of the charge on A is transferred to the capacitor of B because the PD across the capacitors are not equal. And yet they are connected. Now they are like this. but this is 3C, this one is C, but this one was the one which was initially charged. So because this has a different PD than this one, yet they're in parallel, the PD must become equal. So the charge, some charge from A must be transferred to B because the PDs across the capacitors are not equal. But when does transfer of charge stops? Transfer of charge stops when the PD becomes equal. So we shall say transfer stops when the PD across the capacitors become equal. Transfer stops when the PD across the capacitors become equal. So that is what really happens here. So when the PD across the capacitors become equal, now the transfer of charge has stopped. Show that the final potential difference VB across capacitor B is given by that expression. Okay, I think there are two ways of doing this. Let me start with the easiest. So we have now two capacitors which are in parallel with each other. One has capacitance C, another one has 3C. This is A, this is B. They're in parallel. That means the PD across capacitor A is the same as the PD across capacitor B. But remember, the total charge which was on A, total charge which was on A, total charge which was on A, or total charge was given by total charge. Let me call Q total. Total charge was CV before. That is, initial total charge was CV, which was shared later on. So initial total charge is CV, and yet total charge must be the charge on A plus the charge on B. So the charge which is now on capacitor A plus the charge which is now on capacitor B is equal to the initial total charge which was C times V. Okay, but remember, charge is C times V. So the charge which remains on capacitor A is going to be capacitance C of A times the PD across it, which I've just called VB, because VA and VB are the same. Then plus the charge which goes on capacitor B is the capacitance there, which is 3C, times the PD across B, which is the same, which is VB. This is going to be equal to C times V. Okay, so C has cancelled out. So I have VB plus 3VB, which is 4VB, equaling to V. So that means VB is going to be equal to V divided by 4. That's one way of doing this. So they said explain your reasoning. So my reasoning is that total charge is going to be the charge on capacitor A plus the charge on capacitor B, which was initially C times V, as we saw in the original part of the question. Alternatively, I'll use another analogy, or I'll use the concept of total capacitance. Since they're in parallel, total capacitance is the sum of the capacitances, which is C plus 3C. That is 4C. That is if they're in parallel. Then total charge, remember total charge was equal to C times V. Then the PD is equal to charge divided by capacitance. So the PD across A and B is the total PD across both of them is going to be the charge which is C times V, divided by total capacitance, total charge over total capacitance, which is 4C. So this gives us V as, or VB as V over 4 using total capacitances. Okay, determine an expression in terms of V and C for the decrease delta E in total energy that is stored in the capacitors as a result of the change in potential in position of the switch. Okay, so first of all, we have already seen that energy is a half CV squared. Okay, so the total final energy, I'll call it E2, is going to be a half times the capacitance times V squared. So this is a half. The capacitance is in parallel the capacitance, because they're in parallel, total capacitance is 4, so that is times 4C. Then the PD, when they're in parallel, is V divided by 4, and this is squared. The 4, this is V squared over 16. The 4 becomes, so this gives us 1 over 8 times CV squared. That is total energy before. Then initial energy, which is E1, remember it was a half CV squared from the previous part of the question. So the question was determine the decrease in energy. So this is going to be a half CV squared minus 1 over 8 CV squared. So we just check this. 8, LCM is 8. That is 8. So this is going to be 4 CV squared minus CV squared, which gives us 3 divided by 8 CV squared. So the change is 3 over 8 CV squared. That is the answer here. I think I've not written it well. It is 3 divided by 8 CV squared. Okay, that is all about capacitance. I think this is magnetic fields. A heavy aluminium disc has a radius 0.36 meters. The disc rotates with the wheels of a vehicle and forms part of an electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field of flux density 0.17 Tesla is switched on. The magnetic field is perpendicular to the plane of rotation of the disc as shown in the figure. Okay, so if the magnetic field is perpendicular, then there is a force which is experienced according to Fleming's left-hand rule. Define magnetic flux. We know magnetic flux is simply B times A. So it is the product of the magnetic flux density and the area normal to the magnetic field. The product of the magnetic flux density and the area normal to the magnetic field, that is magnetic flux. BA, but remember B and A should be at right angles, so that is magnetic flux. Then calculate the magnetic flux through the disk. Give a unit. Of course, it is measured in Webers. So flux, which is normally written as phi, is B times A. So B is, so since the disk has a circular cross-sectional area, so I'll say B times pi r squared because it has a circular cross-sectional area. B has been given as 0.17 Teslas times pi The radius is 0.36. So times 0.36, and this is squared. So we check with our calculator. 0.17 times pi times 0.36 squared. So that is 0.0692. I want three significant figures, which is going to be 6.92 times 10 to the power of -2. The units, that is Weber. Okay, the disk is now rotating at a rate of 25 revolutions per meter. So 25 revolutions per second. Capture the magnitude of the EMF induced between the axle and the rim of the disk. So we know that EMF induced according to Lenz's law or Faraday's law, the induced EMF is equal to the rate of cutting, of flux, which is actually the change in flux over time. That is the induced EMF. Okay. So calculate the magnitude of the EMF induced between the axle and the rim of the disk. The disk is rotating at a rate of 25 revolutions in 1 second. So the time for one revolution is going to be 1 divided by 25 seconds. Okay, so the EMF is going to be the flux which we have previously, change in flux, 6.92 times 10 to the power of -2 divided by the time, which is 1 over 25 in seconds. So we have 6.92 exponent -2 divided by 1 divided by 25. So that is 1.73. So the induced EMF is 1.73 volts. Then the axle and the rim are connected into an external circuit that enables the energy of the rotation of the disk to be stored for future use. The direction of rotation is shown in figure 6.1. Okay. Use Lenz's law. Remember Lenz's law? The direction of the induced EMF is always such as to oppose the effects causing it. To determine whether the current in the disk is from the rim to the axle or from the axle to the rim. Explain your reasoning. Use Lenz's law of electromagnetic induction to determine whether the current in the disk is from the rim to the axle or from the axle to the rim. Okay, since rotation is anti-clockwise, since rotation is clockwise, let's see. By Lenz's law, using the right hand, the direction of the induced, if I want to know the direction of the induced current, I'll pull out the right hand. So the field, first finger pointing to the right, motion is upwards. As the motion rotates, the induced current is such as to oppose the rotation. So it means the induced current must cause a force which opposes the rotation. Okay, so if now the force is okay, so it means the current in the disk, the force must oppose the rotation of the disk, and that means that force is going to be given by Fleming's left hand rule, and therefore the current must be coming from the rim to the axial. If the current was from the axial to the rim, by Fleming's left-hand rule, that disk will rotate clockwise. But if by Lenz's law it should oppose the rotation of the disk, then the current must be coming from the rim to the axial. So we shall simply say that current in the disk is perpendicular because the field was perpendicular to the disk, so current in the disk must be perpendicular to the field. So current in the disk is perpendicular to the magnetic field, which causes, if the current is perpendicular to the magnetic field using Fleming's left-hand rule, it means the force acts, it causes the force to act on the disk, which causes the force to act on the disk. The current in the disk is perpendicular to the magnetic field, and this is going to cause a force to act on the disk. The disk which is carrying a current is perpendicular to the magnetic field. Okay. So, but by Lenz's law, the force opposes the rotation of the disk. By Lenz's law, this force must oppose the rotation of the disk. By Lenz's law, the force opposes the rotation of the disk. The force opposes the rotation of the disk. So if the force is to oppose the rotation of the disk, then the force will be this direction. The field is in that direction. So the thumb pointing, the first finger pointing to the left, the field, the first finger is pointing to the left, and the thumb pointing towards you. You notice that the second finger points towards the center of the disk, which is towards the axial. So it means by Fleming's left-hand rule, the current is from the rim to the axial. By Fleming's left-hand rule, the current is from the rim to the axial. I just want to demonstrate this further. The axial, remember, is at the center of the rim. So according to Lenz's law, the disk is rotating clockwise. That means the force should be pointing this side downwards. So this is the direction of the force. So remember, when you have your left hand, the three fingers, the thumb is the force or the direction of motion. The second finger is the field. The first finger is the field, and the second finger is the current. So put the first finger to the right, and make sure the thumb points towards you, because according to Lenz's law, the force must oppose the rotation. If the disk is rotating clockwise, the force should be causing anti-clockwise, should be opposing motion. So the thumb points towards you. And if you make the thumb to point towards you, you notice that the second finger is pointing towards the center of the disk or towards the paper. So that means the current must be leaving the disk to the axial. Okay. So I think that is good. Okay. This is alternating current. 4 diodes are used in a bridge rectifier circuit to produce rectification of sinusoidal AC input voltage Vin. The figure shows part of the circuit, but 3 of the diodes are missing. Okay. The PD across the load is load resistor R is the output PDV out of the bridge rectifier. State the name of the type of rectification produced by a bridge rectifier. Of course, a bridge rectifier has 4 diodes. It produces a full wave. So this is full wave rectification. Full wave rectification. Full wave rectification. Complete the figure by drawing 3 missing diodes correctly connected. Okay, so we want a full wave rectification. Let's check. Of course, one thing we need to notice is that if we remember a diamond bridge, if I consider this diagonal here, it means this diode should point in the same direction as this diode here. And therefore, this diode here should point in the same direction as this one, and they should point in the opposite direction, of course. Okay, we can check. I'll remove this diagonal line. If we consider the first half cycle, we can try to consider the first half cycle and see if this is positive and this is negative. So current is going to flow like this. It will continue. This one will not conduct. It will continue up to here. So that means this side will be positive. If we consider the second half cycle where this is positive and this is negative, so current is going to positive, I don't think this is correct. I have to check this. I don't think this is correct. Complete the figure by drawing 3 missing diodes correctly connected. Okay, so I want the output to be full wave rectified. So let me check. Suppose if I want this diode to conduct, let me see if current is to flow like this. It doesn't take this route. If I make this diode to be like this, okay, if this is positive, for the first half cycle, if this is positive, this conducts, current enters here. So this should be facing this direction, I guess. Okay. So if this is positive and current flows like this, taking this route, entering the load, it continues up to here. Then if this is positive, current should take this route. So I think this is going to be like this. So let's check. This is positive. Current flows like this. It doesn't go this way. It enters from here. It continues. It doesn't, of course, it can't go back to where it was positive. So it will come back this side to the negative part. Then if the second half cycle, if this is positive and this is negative, then current is flowing like this. It will go through this. It will take this route. It will continue to this one. Then up to this point here. So I think that is fine. Maybe let me change the colors for the cycles. So for the first half cycle, I'll use a different color to see if there is a complete circuit here for conduction. So supposing this is positive, this is negative. So current will not take this route. It will flow in this route. So the current will flow in this direction, take this route, come to the load, take this route up to the negative. So that cycle is complete. So this will not conduct and this one does not conduct. Those two conducts. So let's check the second half cycle. I'll use red. Second half cycle, this is negative, this is positive. So current will not take this route. So it will be taking this route. So current takes this route and it will flow. It can't take this route, so it will continue. So current is flowing like this through the load. It can't come back to the same point, so it will continue on its way up to the negative point. So this one and this one conducts. So for the first half cycle, we saw that this load diode and this one conducted. For the second half cycle, it is this one and this one that conducted. So let me remove this blue tick here. I want to put a green tick on this one. For the first half cycle, this and this conducted. Second half cycle, this and this one conducted. Okay, so that is a correct analysis. So it means the diodes are now in the correct path, in the correct orientation. So I can now rub off the outer sketches. Okay. So the question is, so we have done this. Draw an arrow to indicate the direction of the current in resistor R. So the current, of course, is flowing in this direction here. So I'll put here an arrow. That is the direction of the current. V in has an amplitude. V in has an amplitude V naught and a period T. And the period T. The figure shows the variation with the time T of V in. On the figure, sketch the variation of V out with the T between T equals to 0 and T equals to 2.0 T. Okay, so remember this is full wave. I'll start with this. If this is V in and it is full wave, if it is full wave, it is half wave rectification. V out, of course, V in has an amplitude V naught and period T. This figure shows the variation with T of V in. But this is full wave rectification, so it means the negative half cycles are inverted. So we shall have this. The negative half cycles are going to be inverted like this. Okay, so that one is very easy because the negative half cycles are inverted. So we shall have 1, 2, 3, 4, 5. So our graph goes to this point. Okay, you can draw something better than mine. It is not a straight line, these are curves. Okay, so that is the graph here for full wave rectification. Then the next part, the power dissipated in the resistor is P. On the figure, sketch the variation of P. Of course, power will never go to will never become negative. So the graph is going to be exactly the same as the one we have just done. Because power is always positive, so it's just going to be exactly the same graph. So I'll just sketch almost the same graph. Since power depends on the square, 1, 2, 3, 4, 5, depends on the square of current, or power depends on the product of I and V, which is always positive. So the power is always positive, so the graph is just the same. Okay, so the graph is almost the same, it's just the same. Remember, power is equal to V naught times I naught, or it is V naught squared over 2R. So it means the maximum power, let me call this one P naught, and the graph of power is always above the x-axis. Okay, suggest with a reason how the root mean square value of V out compares with the root mean square value of V in. So remember, V root mean square is equal to V naught over root of 2. So they are saying to compare how the root mean square value of V out, of course, is going to be the same, because if we look at V out, when it is V naught is the same, let's look at V in. V naught is the same. Since the root mean square is depending on V naught and is the same for both, then the root mean square value is going to be the same. So that is automatically direct. The root mean square value is going to be the same. So we can say V naught, V squared against time graph is the same for both. V squared against time graph is the same for both. V squared against time graph is the same for both V out and V in. So the root mean square value the root mean square values are the same. The root mean square values are the same. Alternatively, you can look at the graph of power, and you notice that power does not depend on the sign of V. So it gives the same root mean square values. because power does not depend on the sign of V, so we have the same root mean square values. Okay, I think that is the same. That is enough. Alternatively, if you were to sketch a graph of power against time, either with or without rectification, the graph would be the same. So it means the root mean square values are the same. So power versus time graphs. Power versus time graph. Let me just say graph is the same with or without rectification. Either there is or there is no rectification. So this means same root mean square values. Root mean square values. Okay. Because power, if every time we sketch a graph of power, it will always be above the x-axis. Since their V naught values are the same, so it means the power time graph is going to be the same whether there is rectification or there is no rectification. So it means the root mean square values will always be the same. Okay, so I think that is the end of alternating current. Then this is quantum physics. The figure shows the lowest 4 energy levels of an electron in an isolated atom. Okay. Figure shows the lines in the emission spectrum of the atom that corresponds to the transitions, the electron from n equals 3 to n equals to 4, n equals 3 to 4, to 1, and n equals to 4, n equals to 1, okay? Explain with reference to the photons why there is a single frequency of electron radiation that corresponds to each of these transitions. Of course, every transition emits just a single photon whose energy is equal to the difference between two energy levels. And each frequency of the radiation corresponds to the energy of the photon. So we can say each frequency, what am I right? I think I'm tired. Each frequency of radiation corresponds to energy of a photon. And we know that transition emits one photon. Each transition emits one photon whose energy is equal to the difference between two energy levels. In other words, the difference in energy is equal to HF. Difference between two energy levels is equal to HF. Okay. On the figure, draw a line that corresponds to the transition of the electron from n equals 2 to n equals to 1. N equals to 2 to n equals to 1. Let's compare this and this. So notice that the difference in energy transition is directly proportional to the frequency. So that is the difference in energy is going to be correspond to the deviation in the frequency. So A smaller energy transition will give out a photon which has a lower frequency. So the next line is going to be is going to be to the left. But then the change in energy from n equals 2 and n equals 3 is very small compared to the change in energy from n equals 3 to n equals to 1 and n equals 3 to n equals to 1. So it means the deviation is going to be bigger on the left. So I'll draw a line to the left, which is where this deviation is relatively bigger than the one which was the gap is bigger than the gap which was there before. And I said label this line A. So this is line A. Then draw a line that corresponds to the transitions from n equals 3 to n equals to 2. N equals 3 to n equals 2. This is a much smaller frequency because the change in energy is directly proportional to frequency. It is a much smaller frequency. That means the deviation from the line we have drawn is going to be bigger. So this is going to be another bigger deviation. So I will put it here. So this is going to be my line B. Okay. Then the frequencies, I think I've not skipped anything. Okay. The frequency of the radiation represented by the line A is FA. The frequency of radiation produced by line B is FB. The energy of the ground state n equals to 1 is E1. Determine an expression in terms of FA, FB, E1, and the Planck constant H for the energy E3 of the energy level n equals 3. So remember the difference in energy is equal to the difference in the energy level. So let this be E3 minus E1. Okay, we have E1 and E3. Okay, so let's consider line A. For line A, which for the line that I labeled A, transition was from E2 to E1. E2 to E1, which is equal to H times the frequency, which is called FA. Then for the line that I labeled B, the transition was from E3 to E2. That means this is going to be H times frequency FB. Now I'm going to add these two equations. When I add these two equations, I have that E3 minus E2 plus E2 minus E1 should be equal to H FB plus H FA. So it was cancelled out. Therefore, we have that E3 minus E1 is equal to H into FA plus FB. And there is an E1 here, so that is plus E1. Oh no, it is still on the left hand side. So we want to make E3 the subject, so I'll just take this the other side and say E3 is equal to E1 plus H into FA plus FB. So the answer here is simply E1 plus H into FA plus FB. Okay, as simple as that. Then next is nuclear physics, I think, and radioactivity. Define mass defect. What is mass defect? That is the difference between the mass of the nucleus and total mass of the nucleons when the nucleons have been separated to infinity. So this is simply a difference between the mass of the nucleus and total mass of nucleons when the nucleons are separated to infinity. That is what we call mass defect. The table shows the mass defect of 3 nuclei. Okay. The nuclear fusion process in a particular star is described by this equation, that is deuterium, tritium, to give us helium plus X, where X is a particle that has no mass defect. State the name of X. We can try to balance. So here it is 2 plus 3, that is 5. So this should be 1 to make it 5. And this should be 0. And I think this is a neutron. So this is a neutron. So that the energy released when one nucleus of helium is formed in this fusion reaction is equal to that. First of all, we know that energy is given by mass defect times c squared. We first find the mass defect. So let's find total mass on one side, which is 0.0303777 minus the total mass on the other side, which is 0.09105 plus 0.002388. Okay, so let's find the mass defect first. 0.030377, 0.009105 plus 0.002388. So this is 0.0188, another 8 and 4 in unified atomic mass units. So let's find now the energy. The energy will be 0.018884. We are changing the mass to kilograms, so I'll multiply by 1.66 times 10 to the power of minus 27. Now it is in kilograms times the speed of light. 3 times 10 to the power of 8, but this is squared. So I'll multiply this by 1.66 exponent minus 27 times 3 exponent 8, but this should be squared. So this is 2.82 times 10 to the power of minus 12 in joules. So that is already shown. Okay. So the star in B has a radius of 2.3 times 10 to the power of 9 meters and a luminosity of 1.4 times 10 to the power of 28 watts. All the energy released from the formation of helium is radiated away from the star. All the energy that is radiated from the star is being released in the form of helium. Determine the mass of helium produced per unit time by the fusion process. So let's first of all find the number of atoms per unit time. So number of atoms produced per unit time. Number of atoms produced per unit time. How do you find number of atoms? Remember, number of atoms, we said number of moles is mass over molar mass, which is number of atoms, divided by, this is divided by Avogadro's number. But then they said the star in B has a radius of 2.3 times 10 power 9 meters, and a luminosity of 1.4 times 10 power 28 watts. All the energy released from the formation of helium is radiated away from the star. All the energy that is radiated from the star has been released in the formation of helium. So it means if I want to know the number of atoms by any time, then I will get the energy, which is 1.4 times, because the energy has been released as helium, so it is 1.4 times 10 to the power of 28 divided by, let me check the number of the energy of each helium, which is 2.82. So this is 2.82 times 10 to the power of minus 12. So this is going to be the number of atoms per second. So we have 1.4 exponent 28 divided by 2.82 exponent minus 12. So this is 4.96 times 10 to the power of 39. 4.96 times 10 to the power of 39. That is the number of atoms per second. Okay, let's find the mass of an atom. The mass of one atom. Of course, one atom of helium has a mass of 4U, that is 4 times U, which is 4 times 1.66 times 10 to the power of minus 27 in kilograms. Alternatively, I could use this N over Na times the molar mass, which would give me the same answer. So this is going to be 4 times 1.66 exponent minus 27. So that is 6.64 times 10 to the power of minus 27 kilograms. That's the mass of one atom. So determine the mass of helium produced per unit time. We know that we now know the number of atoms which are produced per second, and now know the mass of each helium. So mass per unit time it's simply going to be 6.64 times 10 to the power of minus 27, then multiplied by 4.96 times 10 to the power of 39. 4.96 exponent 39. So I'm getting 3.3 or 3.29 times 10 to the power of 13. Okay, then the surface temperature of the star. Of course, there I will use luminosity. I know that luminosity is 4 pi times sigma times r squared times t to the power 4 according to Stefan Boltzmann's law. So I want to find the temperature. So T power 4 is going to be the luminosity, which is 1.4 times 10 to the power of 28 divided by 4 pi. Sigma is Stefan Boltzmann's constant, which is 5.67 times 10 to the power of negative 8. Then the radius was given as 2.3. 2.3 times 10 to the power of 9, and this is squared. So let me first simplify this. 4 pi times 5.67 exponent minus 8 times 2.3 exponent 9, but this is squared. So I'll have 1.4 exponent 28 divided by the answer. Then I have to get the fourth root. Let me check the fourth root. Okay, so I'll say fourth. No, that is not the fourth root. Shift fourth root of the answer. This will be 4. Fourth root of the answer. So this is 7,800. So T is equal to 7,800 when I find the fourth root. Okay, so I think that is fine. And final question. This is medical physics. State the name of the charged particles that are accessed by the applied PD. Of course, these are automatical electrons. X-rays are used in medical diagnosis, and they are produced in an X-ray tube. In the X-ray tube, charged particles are accelerated towards the metal target. These charged particles are electrons. Explain how X-rays are produced at the metal target. So when the fast moving electrons hit a metal target, when fast moving electrons hit a metal target, they are rapidly decelerated, of course. They are rapidly decelerated. They are rapidly decelerated. They are rapidly decelerated. Of course, they have lost the kinetic energy. So the kinetic energy lost by the electrons is emitted as X-ray photons. The kinetic energy. The kinetic energy lost by the electrons is emitted as X-ray photons. Okay, so the kinetic energy which the electrons lose is emitted as X-ray photons. But remember, not all the energy is actually 99% of the energy becomes heat. Only 1% becomes X-ray photons. So the kinetic energy lost by the electrons, I'll put here 1%. About 1% becomes X-ray photons. We calculate the minimum wavelength of X-rays produced when the applied PD is 5.8 kilovolts. Okay, so we know that energy of the photon is HF, and this is going to be HC over wavelength. But remember where this energy comes from. It comes from the kinetic energy of the electron. So we shall say E times V is HC over lambda. So the wavelength is going to be HC divided by E times V. So I will just substitute. H is 6.63 times 10 to the power of minus 34, then times 3 times 10 to the power of 8 divided by 1.6 times 10 to the power of minus 19, then times 5.8 kilovolts, that is 5,800. I'll check my calculator. 6.63 exponent minus 34 times 3 exponent 8 divided by 5,800 times 1.6 exponent minus 19. So this is 2.14 times 10 to the power of negative 10. Okay, so that is going to be the wavelength, 2.14 times 10 to the power of negative 10. And the last part of the question, X-rays pass through a medium that has an attenuation coefficient of 1.4 per centimeter. calculate the percentage of the X-ray energy that is absorbed by a 2.8 centimeter thickness of this medium. Okay, we know that intensity transmitted through a medium is equal to I naught e power negative mu x. Remember, I is the intensity transmitted, I naught is the instant, mu is the linear attenuation coefficient, and x is the thickness. So the intensity transmitted over the instant intensity is going to be e power negative. Mu is 1.4. I will not change the units because this is per centimeter and this is centimeter. So I'll just say times 2.8. So this gives me e so e power, I'll put a bracket, negative 1.4 times 2.8, close the brackets. So this is 0.0198. Okay, that is the intensity transmitted. So this is the fraction transmitted. So this is fraction transmitted. Then our fraction absorbed. Of course, fraction absorbed is going to be 1 minus alpha, this 1 minus what is transmitted. So it is 1 minus 0.0198, which is 0.9802. Okay, so as a percentage, so this becomes 98.02%. So this is going to be 98%, just multiply by 100. Okay, I think I've tried my level best to keep time on this. I've tried to give more explanations. In the case of anything which is not clear, I may have made a few mistakes. You can always write a comment and give this video a thumbs up and comment, like and share. Until next time, bye bye.